Right, the next topic in chapter 7 here is internal forces. Okay. So far we've only really looked at forces that are acting on a beam or an object, or that a beam or an object exerts on another one. Now we're going to start looking at what happens inside these beams, inside these structural elements, after these forces are applied. So I could take a look. So you've got a beam of rectangular cross section. Okay, what I'm going to do here is, if I want to find out what the internal forces are, the internal stresses right in the middle of this thing are, I'm essentially going to cut it right down the middle and split it into two pieces. Okay, so the left-hand side will be over here. Right-hand side's over here, and this is the surface that I've cut and separate out into two pieces. Okay, so whatever forces are acting in here, similar to the Newton's third law relationship, where we have two beams interacting or two other objects interacting, we're going to treat these as two objects that are interacting at this point. Even though in reality it is a single object, we can treat it as two parts of the same object, the same relationships apply. So we end up with forces here acting between these two. Okay, we can have a tension or compression force. That's what's called the normal stress. And it's going to act on both, again, opposite directions, both ways. Okay, we typically draw, sign conventions here are going to be a little confusing at times, but they typically draw that this beam would be in tension is going to be the positive normal force. Okay, so again here, in tension is going to be the normal force on both pieces. We're also going to have a shear stress. Okay, normal is trying to either pull it apart or push it together. Shear is trying to rip it sideways. Okay, so we're going to have a shear force. That gets a symbol V. Okay, not to be confused with velocity or volume or any other things we use V for. V is shear stress in this case. And again, the positive direction for shear stress is drawn so that each individual piece would have a tendency to rotate clockwise. This is confusing because when we typically talk about moment in a right-handed coordinate system, when we talk about moment in a right-handed coordinate system, we talk about clockwise being negative. When we talk about a shear force, okay, this beam with this would tend to rotate clockwise, this beam would tend to rotate clockwise. We end up with positive moment in each direction. Okay, so we end up with normal there, normal there. We end up, and then we also have a moment applied because we can cause this thing to twist or bend here as well. So moment, where moment's given a positive direction so that it tends to bend in a concave up direction, if it helps you remember it. Trying to bend this beam into a smiley face is the positive direction. And then we're going to, so this is moment here, and then we're going to have the same thing here again, trying to bend it up. So we have normal, left and right canceling, shear up and down, and moment counterclockwise and clockwise canceling. So that's what our diagram would look like. So then what we would do is we'd look at each of these pieces, or separately, or again, always separately. We do equilibrium relationships for this one or for this one, and solve for these shear, normal, and moments. Okay, the internal shear, the internal normal force, and the internal moment on this beam at this point. There is a three-dimensional version of this, which is a bit more messy, but I'll take a look at that. If this, instead of just a rectangular cross-section, say we make this a solid cylinder, okay, we still cut it down the middle. Okay. Actually, I'm just going to draw one side of this because this does get messy. We have one normal stress. Nice and easy there. Okay. We're going to have two shear stresses. We're going to have our typical shear stress in the vertical direction. Okay. And then we're going to have a shear stress acting in the third direction here. So if I were to do my coordinate axes, X, Y, and Z, the way I've drawn this, the normal force acts in the y direction. I have stress in the z, so shear in the z and shear in the x. I'm also going to have moment. Now I'm going to have, just as I have a force in each of the three directions, I'm going to have moment about each of the three directions. So that gets messy. So moment about x is what we've done before. That's just going to be moment about x. Moment about z is going to cause it to rotate about like this. So moment about z is going to go like this. And then moment about y is what's called a torsional stretch, because it's going to cause it to twist. Okay? Whereas moment about z, moment about x are causing it to bend in one direction. The moment about y is going to cause it to twist. So that's going to be like this. Okay, we don't do much in this course with three-dimensional shear and moment here, three-dimensional internal forces, but I did want you to see kind of how this works. The analysis is the same. Obviously, it's just, again, we're dealing with six terms instead of three when we switch to three dimensions. Okay, but we won't do any particular problems with the three-dimensional setup. We'll stick to two-dimension in this course at least. So I will move on to an example. We'll start pretty simple here. Okay, the example here we have, let's see, we'll take a simple beam. Okay, we're going to pin join it at this end, and put a roller over here. We're going to put a, so this will be point A. We'll have force applied force of 6 kilonewtons here. And then at the end, we're going to have an applied moment of 9 kilonewton meters. Okay. In terms of dimensions, now we'll call this point B and this point C. In terms of dimensions, we'll call this, I'm going to go with 4 meters and 5 meters. Okay? And what I'm going to ask is, find the internal forces just to the left and right. Of point B. Okay, the phrasing here is kind of particular. All right, it says just to the left of left or right of point B. The reason that we do this is we have idealized this force. We have said this force only acts at a single point on our beam. In reality, if you exert a force on something, it's always distributed over some area. Even if I push with my finger on the board, there is some small area that my finger is covering as I press down. Here we're idealizing this to a single point. Okay, so when I try and cut this beam, I can't cut it right on the force. That becomes an undefined problem. I either have to move a tick to the left so that the force is on the right-hand side of the cut, or a tick to the right so that the force is on the left-hand side of the cut. Okay, we're assuming that's some tiny distance, negligible distance, so that this is still 4 meters and 5 meters. It's just which side of the cut do we want to put the extra force on, that 6 kilonewton force on. Okay, but before I get to this, we are going to need to know what the support forces are on this die. So we'll solve for that first. Okay, so support forces, this is, we have a pin joint at A. we have AY, AX. At C, we have a roller, so we have CY. Okay, so from here, we can go ahead and start looking at summation of forces. Summation of forces in the X is going to give me that AX equals 0. Easy enough, we can just take that out. Okay, summation of forces Y, we have too many unknowns. What I'm going to do is take moment about, I can take moment about A or C, it doesn't matter. Summation of moment about A is equal to 0. AY drops out. The 6 kilonewton force is minus 6 times 4. We have plus CY times 9, plus we have our 9 kilonewton meter applied moment at the end. Okay, so AY dropped out. We have the two forces and the applied moment. Solve this. We get CY equals 24 minus 9, 15 divided by 9 is 1 2/3. Yeah, 1.67 kilonewtons. So then summation of forces in the Y gives us the AY minus 6 plus CY equals 0. So if CY equals 1.67, that means AY equals 4.33 kilonewtons. Okay, so from there, we can label these in here. So AY was 4.33, and this is 1.67. All right, so we have our support forces. At this point, we need to slice the beam, look at it in 2 pieces, and analyze from there. Okay, so what I'm going to do is I'm going to draw the beam in its 2 pieces. Okay, this we're going to cut cut just to the left of B. Okay, and then we're going to have the other half over here. So over on this edge, we still have 4.33 kilonewtons. Since we cut just to the left of B, that means the 6 kilonewtons is on the right-hand side. We still have our 1.67 kilonewtons here and our 9 kilonewton meter applied moment. Okay. So we need to include our internal forces here. So we end up with normal, shear, and moment, and the same on the other side. Okay, but we really only have to analyze one or the other. Again, normal, shear, and moment are going to be the same on both sides, just opposite directions. Okay, the right-hand side has a lot of stuff going on. The 6 kilonewton force, this 1.67 support force, and over here we've only got one force to deal with. So we're going to work with that. Okay. In reality, you can bounce between the two, work with both sides if you need to, if one's easier or not. But for here, I'm going to work, for this example, it's easier to work exclusively with the left-hand side. Okay, so this becomes pretty straightforward. We're just looking at the equilibrium equations here. We have summation of forces in the X. Okay, it is important to note here, when I cut this, even though I said just to the left or just to the right, this is still 4 meters. Okay, when we deal with this idealized point force here, we can move just a tick to the left or just a tick to the right, some infinitesimal distance that gets us just off the force, but still at 4 meters. Okay, this is sort of a construct of when we start idealizing forces and distances and stuff, we end up with this sort of thing that may not make intuitive sense to you, that we're actually moving a little bit but not changing our distance. But it's because we're dealing with an idealist situation where the differences are considered negligible. Okay, it is a good strategy for analyzing this sort of thing. Okay, so summation of forces in the x is quite easy. 0 is equal to normal force, so there is no normal force on this beam. Shear. Well, we can get that, so summation of forces in the y equals 0 is 4.33 minus v. Well, that gives us that v, their shear force, is 4.33 kilonewtons. Okay, and when we look at the moment, you can take moment about any point you want. Okay, note that you still have to include these forces if you take moment here. I'm going to take moment about point A, sure. You either want to take moment about point A or moment about point B over here. Either way, it's not going to make a difference. But moment about point A, this 4.33 drops out. So we end up with, this is going to be clockwise, so minus V times 4, plus M is in counterclockwise direction, so that's there. Well, we know V already, so this turns into 0 equals minus 4.33 times 4 plus M gives us that M is equal to 4 times 4.33 is 17 point something. 17.33. Okay, so just to the left of B, if you think about this force, just to the tick here, we have no normal force, no normal internal force. We have an internal shear force of 4.33 kilonewtons, and we have an internal moment, trying to make it bend, of 17.33 kilonewton meters. Okay, these internal forces are important because later on, if you go into a strength of materials, you have to decide whether or not these internal forces are enough to cause bending or breaking or deformation in our material. Okay, so we will continue to, you will start seeing these again long term. But we also have to look at, the problem also specified, cut just to the right of B. So that's going to look just a bit different. So leaving these alone, I'm going to write these over here. We end up with normal equals 0, shear equals 4.33 kilonewtons, and moment is 17.33 kilonewton meters. Okay. So now we're going to cut just to the right of B and see how that works. Okay, we still have our 4.33 here. Now we've cut just to the right of B, so our 6 kilonewton force is on the left side. Right hand side here we have nothing there. We have a 1.67, and we have an applied moment of 9 kilonewton meters. All right. So we again have to include our shear and moment pieces. We have normal, shear, and moment. Okay, now it doesn't really matter which side we look at. Both this side has got two forces. This has a force and a moment. I'll take a look at the right-hand side this time, just for the sake of varying it up a little bit. You will get the same answer regardless of which side you look at, or if you look at both, you'll get the same result. Actually, that might be worth showing. We'll do that. Okay, so going through this a little bit quickly since we've seen this just a few moments ago. we'll show that it does give us the same result either way. So summation of forces in the x equals 0 is n, so n equals 0. Fine. Okay, summation of forces in the y equals 0 equals 4.33 minus 6 minus v. That gives me that v is equal to, okay, it is now a negative 1.67 kilonewtons. Okay, notice we are getting a different answer when we cut just to the right of b than we did when we cut to the left. What I say we're going to get the same results as when we look at this piece and we look at this piece. And v and m are going to end up the same. So taking moment about, I'm going to take moment about the center here. So summation of moment about b, so that the 6 and the v drop out. Okay, equals 0, equals, this is going to rotate clockwise, so minus 4.33. This is still 4 meters times 4 plus m. Okay, we end up with those two dropping out, so we end up with m equals, I'm trying to keep this on the board here, so m equals 4 times 4.33 is our same 17 kilonewton meters. Looking at the other side here, we're going to do the same thing. We're going to have summation of forces in the x equals 0. Same thing, n equals 0. Summation of forces in the y equals 0. Now we have v is positive plus 1.67. So v is going to equal negative 1.67 kilonewtons. So far, so good. We're going to take moment. Again, it doesn't matter where I take moment about. I'll take moment about point C. Okay, so we have v times, well, this distance was 5. So we have v is going to go clockwise, so minus v times 5 plus m, minus m plus 9. Plug in your v of minus 1.67. This gives you a moment. This gives you that m, our internal moment, is going to be, it should end up equaling 17.33 again. 1.67 times 5 is 8.33 plus 9 is 17.33. So we get the same thing. Again, it doesn't matter which side of the diagram you choose, you're going to get the same answer regardless. The one thing that is worth noting, the moment didn't change because as we move from one side of the force to the other. Notice that the force did. The shear force went from 4.33 just to the left to a negative 1.67, i.e. the force dropped. The shear force had a decrease of 6 kilonewtons from 4.33 upward to 1.67 downward. That's to be expected when we cross over a 6 kilonewton force downward. We're going to see our shear force decrease by that same 6 kilonewtons. Okay. So this is a simple example. I did some extra work here to show that it's equivalent either way. But this is a simple example of how to find an internal force on a simply loaded tube. There is one piece that gets a little bit more complicated, and that's when we have to deal with a distributed load. Okay, if we look at an example with a distributed load, say a simply loaded beam here, or not so simply loaded, I guess. This is still going to be a pin joint. This is still going to be a roller. Okay, we're going to have a distributed load, triangular in shape. Okay, and this is going to be 4 kilonewtons per meter. And that trends all the way down to 0. Okay, this is going to be, label points here. This will again be point A. Point B will be right smack in the middle. And point C will be over here. In terms of dimensions, 3 meters, 3 meters. Okay? And what I want to know is find the internal loading, find the internal forces. At B. In this case, I don't have to specify just to the left or just to the right. It's just you can't find, because of the assumption of a point force, we cannot take internal forces right at a point force. So if we have a point force in our problem, we have to move, or a point moment, we have to move just to the left or the right. Okay, in this case, we have no point forces. Everything is just the distributed load. Okay, the first piece again is going to be finding out. So we are, because it's just the distributed load, we are allowed to find the internal forces at B. There's nothing at B that makes us shift a little bit either way. But again, we need to start with our support forces. Okay, summation of forces in the x is going to get us to the x equals 0. We'll drop that out again. We care about AY and CY. Okay, well, distributed load, we simplify this into a single force. So our single force, the magnitude is going to just be the area of this. It's going to be 1/2 times 4 times 6 is 12 kilonewtons. All right, and so that's the area. In terms of where it's going to be, if we're at 6, it's going to be 2/3 of the way over. Our single force is going to be 12 kilonewtons at a distance of 2 meters from that edge. Okay, that makes things a little easier. So now, with my simplified distributed load, I can do summation of forces in Y, summation of moments. Well, I need to take summation of moment in order to find one of the supports. So I'll take summation of moment about A is equal to 0. So AY drops out. I have, going clockwise, 12 kilonewtons from the distributed load times 2 meters. That is clockwise, so that's negative. Going counterclockwise, I have CY times the whole distance is 6. 24 divided by 6. CY equals 4 kilonewtons. Summation of forces in the Y is equal to AY minus 12 plus CY. That all equals 0. CY is 4. This means AY must equal 8 kilonewtons. All right, so this is 8 kilonewtons, and this is 4 kilonewtons. All right, so that's easy enough. Now when I cut this thing into 2 pieces, at B, okay, the one catch here, the one point that you really have to be careful about, and that does make this a little bit trickier, we have our 8 kilonewtons here, we have 4 kilonewtons over here, we have all our internal forces, which I'll draw just like we normally would. It's a distributed load. We simplified this to a single force. Okay, we can't just put that single force over here. The reason we can't is because some of this distributed load is actually over on this piece of things. Okay, so we need to account for that by splitting the distributed load into the two pieces and then re-simplifying. So I actually have a distributed load on this beam as well, okay, on both halves of the beam. So we end up with a small distributed load here, and then the other piece of it over here. Now we need to simplify those individually. This one is now a trapezoid, okay? This one doesn't look like a lot of fun. This one is a simple triangle. This one we could simplify it. I could find the area of this piece. This is 4 up here. Halfway through this is going to be 2 kilonewtons per meter. This is 4 kilonewtons per meter. This is the same 2 kilonewtons per meter. Okay, I could do this. I would have split this into a rectangle and a triangle and reduce the distributed load and go for that. I'm not going to bother doing it the long way. I'm going to just take a look at the right-hand side, which is going to be a bit easier. This distributed load, 2 kilonewton meters, F equals 1/2. The base is now 3 times the height is 2. This is 3 kilonewtons, and its location is 2 meters from the end. So I'm going to replace this piece of my distributed load by a single force that's 2 kilonewtons. And because it was a triangle, it's 2/3 of the way to the high end. So we're there. Okay? So, and I erased my shear. So now I need to find normal shear and moment as I would normally. So I'm going to go ahead and do summation of forces in the x equals 0 equals n. You will see this trend a lot. A lot of our beams, the normal force is going to be 0. Summation of forces in the y is going to give us that v minus 2 plus 4 equals 0. So that means our shear is a negative 2 kilonewtons. And then I'm going to do summation of moment. It doesn't matter any of the 3 points. I'll take summation moment about B equals 0. That equals 2 kilonewtons, that's counterclockwise, times 1 meter, plus the counterclockwise 4 times the total distance here is 3 meters. M is clockwise, so that gets a minus m. Separate that. Alright, so plugging in here we have 0 equals minus 2 plus 12 minus m. Okay, so we have m equals 10 kilonewton meters. Okay, so I found the shear and moment at that cut in B. If we went and did the other side, it would be an extra step to reduce the distributed load. That's a trapezoid now instead of a triangle, but we would get the same results whether we looked at either side or the other. Okay, so that's where we're going to wrap up looking at internal forces at specific points. More often than we want to know what the stress is here, we're going to want to know what the stress is across an entire beam. And that leads us to something called shear and moment. Diagrams. Okay. This gets a little bit more tricky in that now instead of looking at a specific point, we're essentially looking at it along the entire beam and creating a graph along the length of the beam that works, that sorts this out. So we'll start with a really simple one. We'll go back to a simply loaded beam here. Okay, so we've got our beam. It's going to be the same sort of setup where we have a pin and a roller, and we're just going to put one force in here. Just try and make things a little easier. We'll make that 9 kilonewtons. Dimensions 2 meters, 4 meters, points A, B, just for the sake of things. Okay, we're going to have support forces here, as we always do. At the pin, we're going to have AY, and again, AX, I'll include it, we're going to end up dropping it in a moment. And BY. Okay, again, summation of forces in the X, AX equals 0, it comes right out. Same thing with finding support forces as we've done a dozen times before. Okay, two unknowns in the Y, summation of moment about point A equals 0 is minus 9 times 4 for the clockwise moment due to this guy, plus By times 6. Okay, this gives us that By is equal to 6 kilonewtons. Summation of forces in the Y equals 0 is AY minus 9 plus BY. This gives us that AY is equal to 3 kilonewtons. So I'll label those in there. All right. So the other thing we need with a shear moment diagram is we need to establish kind of a length coordinate. So what I'm going to do is I'm going to say this is distance x. So what I'm going to do is I'm going to find my shear and my moment along this beam as a function of x. Okay? This becomes a little tricky. So what I'm going to do here is I'm going to start looking at where I cut this piece. So I cut here, and I have the other half. All right. I'm going to have a 6 kilonewton force over here. I'm going to have a 3 kilonewton force over here. Now, the question becomes, where does this 9 kilonewton force go, on the left or the right? That depends on where on the beam we're looking. If we're looking at x from 0 up to 4 meters, that means the 9 kilonewton are still going to be over there. If we're looking at from 4 to 6 meters, that means the 9 kilonewton force is going to be over on this side. Okay, so what we need to do is we're actually going to do two diagrams. We're going to do one that applies from 0 less than x up to 4, where we end up putting the 9 kilonewton force over here. Okay, so this applies when x is 0 to 4, and the 9 kilonewton force is going to be over there. When we do we're in a minute here, we're going to do another diagram that's going to apply for x equals 4 to 6, where we're going to have the force over on this piece. Okay, so what we do here is now we add in our internal forces as normal, N, B, and M, and then N, B, and M. Okay, the important thing is here is this diagram would work anywhere in this range. So what I'm going to do is I'm going to call this distance x. Okay, so that means when x is 0, I'm going to be right at the edge here. When x is 4, I'm going to be right in the edge here. But we're still going to have a 3 kilonewton force on this edge, internal forces wherever we cut it, then the 9 and the 6 over on the other side. So we go with this here. If I wanted to analyze this side now, it's important to notice that this is our entire beam 6 minus x. Okay. In this case, it looks a lot easier to analyze the left-hand side, so that's what I'll do. And we'll go ahead and find the shear and moment and diagrams here. Okay, when we're doing shear and moment, notice I'm calling it shear and moment, not normal shear and moment. Normal doesn't usually change much as we go across the length of the beam. So for that reason, we generally don't care about normal when we're doing this. You can certainly find it the same way we did when we were looking at individual points. But for this, generally because it's the moment in the shear that changed dramatically over the length, and because, and this is the bigger reason, when we talk about beams being under stress, they're much more likely to fail in terms of bending or shearing than they are in terms of being stretched apart or crushed lengthwise. Okay, beams will buckle or fold or bend before they generally get stretched out or compressed. So we generally look at just shear and moment. So looking at the left-hand side here, I'm going to do summation of forces in the y is equal to 0. It's equal to 3 minus v. This gives me the shear is 3 kilonewtons. Summation of moment, we'll do summation of moment about the end here. You can take summation of moment about this point. So about the cut, we'll do that. Okay, so summation of moment about the cut, we end up with, this is going to go clockwise, so minus 3 times x. And then we have plus m. No moment due to the shear there. Oops, this equals 0, which then equals negative 3x plus m. So m is going to equal 3 times x. Okay, so we found our shear and moment relationships from 0 to 4. So we have from 0 less than x less than 4. We have that shear is 3 kilonewtons and moment is equal to 3x, and the units are kilonewton meters. Okay, so essentially what was shown here is that from 0 to 4, anywhere in this range, the shear force, the internal shear force is 3. Within this range, the moment increases. So if we're at x equals 1, we have a moment of 3 kilonewton meters. When we're x equals 2, we have 6 kilonewton meters. X equals 3, we have 9. Until we get to x equals 4, we get to 12 kilonewton meters. Okay, so we found the relationship for shear and moment in this section of the beam. We do need to look at the other side. What happens when we cut it so that the cut is past the 9 kilonewton force? Well, that's when we look at the range between 4 and 6. In that case, the beam is going to look like this. Same thing here. We still have our 3 kilonewtons here. We still have 6 kilonewtons here. Now our 9 kilonewton force is here. This distance is 4 meters. Okay, and we still have, oops, I'm going to leave normal out. I'm just going to do shear. Shear, and then moment. Okay, that's shear and moment there. So this distance is still going to be x. This is still going to be 6 minus x. Okay, the only thing that's changed here is because we're now looking at this piece of the beam, we're cutting it in here, the 9 kilonewton meters over on the left-hand piece. So now, this gets a little messy. We can decide what we want to do here in terms of which one's a little easier to deal with. This one we've got an extra force to deal with. On this one we have a moment arm of 6 minus x. Either way will work the same. And I'm actually going to show both because I think that's going to be important in terms of seeing what we get here. So summation of forces in the y is 0, is 3 minus 9 minus v. So this gives us that v is equal to a negative 6 kilonewtons. And summation of moment, Okay, where it makes sense to make this, I'll make it about the cut. Equals 0 equals, this is now clockwise, so minus 3 times x. I'm not going to do that because I don't want to deal with that piece. I'm going to do the moment about A. Okay, simply because I didn't want to have to calculate this moment arm if I took the moment about that piece. So a moment about A, we have the 9 kilonewton force rotates this way, so that's clockwise, so minus 9 times 4 plus, this is going clockwise, so sign minus, V times X plus M. Okay, so we end up with, V is minus 6, so we end up with 0 equals minus 9 times 4 is 36, minus a negative 6, so plus 6x plus m, so m equals minus 6x plus 36. I'll write that up here. So from 4 to x to 6, we have V equals negative 6 kilonewtons and moment equals minus 6x plus 36. Okay. So I am going to take a look and show that this does work out the same on the right hand side. We will get the same answer. It's going to be a little quicker. Summation of forces in the y equals 0 equals V plus 6. So that gives me V equals minus 6 kilonewtons. Summation of moment, now it makes sense to take, it doesn't matter, I'll take moment about the cut, is equal to, well, the shear force drops out, so this is going counterclockwise. This is 6 times 6 minus x, and this is minus m. Okay, so m equals 6 times 6 minus x, which is 36 minus 6x, which is the same minus 6x plus 36. So it turned out the right side was actually a little quicker in this case, but either way, we end up with the same answer. Now, so the reality is we haven't actually started producing a shear and moment diagram yet. What we've got here are shear and moment equations. This is a kilonewton. But the diagrams are simply just graphs. So what I can do here is graph shear as a functional length. 1, 2, 3, 4, 5, 6 meters long. Okay. So the shear is 3 for the first from 0 to 4. And then it drops down to negative 6. And do this little, scale this a little differently. So 4. And then we drop straight down to negative 6. Stays there for the last 2 meters. Okay, so this is my shear as a function of the length of the beam. So the shear stays at positive 3, and then when this force hits, it drops by 9, and then we have negative 6. Okay, moment, same idea, we're just producing a graph. This one is going to be a bit different in terms of the size, so this is going to stay positive the whole time. So I'm going to do this. Okay, and we're going to go as high as, make this 5, 10, and 15, and this is kilonewton meters This is kilonewtons. Okay, so we start out with 3x from 0 to 4. So we're going to try and keep these lined up as much as possible. So from 0 to 4, we're going to graph 3x. So it's 1. So it's 0 at 0. At 1, we're going to have 3. At 2, we're going to have 6. 3, 9. 4, 12. We're going to have a nice straight line here. Okay. And that should be on the line. Then what's going to happen is we're going to have minus 6x plus 36. Or 36 minus 6x. That's fine. We're going to go from 2 more points here. Now, we should only have these discontinuities, okay, in shear when we have a force applied. We should only see discontinuities in moment when we have a moment applied. We don't have an applied moment in this problem. So in theory, this point should stay continuous. So at x equals 4, well, we have 36. We have 4 times 6 is negative 24 plus 36 is 12. So we end up at the same point, which is good. That's a little bit of a sanity check here. If you don't have an applied moment, then this should remain continuous. So we end up with, that is actually an important detail here, so I'm going to slow down for a second. When we have an applied force, we're going to see a discontinuity in the shear diagram equal to the size of the force. No discontinuity in the moment diagram. When we have an applied moment, we're not going to see a discontinuity in the shear diagram. It's not going to have this vertical jump. But we will see a vertical jump in the moment diagram equal to the size of the applied moment. So that's a good way to kind of keep yourself with a sanity check there. Make sure that you have discontinuities in the right places and that they're they are the right size. So this becomes minus 6x plus 36, minus 6x plus 36. Well, 5 times negative 6 is negative 30, so this is 6. Then we end up back at 0 here. And we're back at 0. And again, those rules about continuities and discontinuities apply at the ends as well. Notice we started at 3, ended at we started at 3 where we have a 3 here. We ended at 6 where we have a 6 here. Here we don't have any applied moments at the end, so we started at 0. Okay, so this is a simple problem here. Simple shear and moment, which doesn't, where we're just simply coming up with an expression, an equation, and then a graph of the internal shear and moment in this beam over its length. The one other thing we can run into here is when we have a shear moment diagram involving a distributed load. And that's the last thing we need to look at here. Okay, so that does add one little bit of complexity into the end of this chapter. So if I have a problem that looks like this, I'm going to make that a little longer. Meter. Okay, so we have our typical pin joint right here, and a roller at the other end, and say we have a distributed load that looks like this. Make that 8 kilonewtons per meter. And then at point here, we're going to have an applied moment of, say, 20 kilonewton meters. All right, and label some points here. We'll call this point A and this point B. Give you some dimensions. This will be 5 meters. This will be 1 meter. And this will be 1 meter. All right. So with this type of problem, we need to, again, split it into pieces based on what our diagram is going to look like, where we're going to cut this thing as we move down our x direction here. Okay, so as we started this left edge, okay, we're going to keep moving this way. Nothing changes, nothing changes, nothing changes, nothing changes, till we get to the end of the distributed load. At that point, the distributed load goes away, and we're left with the rest of the beam. So the first range we can look at is between 0 and 5 meters. Okay, because no matter where we cut it in this range, we're going to have the support force at A on one end, we're going to have the support force in B and the 20 kilonewton meter applied moment on the other side, and we're going to have some of the distributed load on either side, and we'll work that out. Before we go on with this, though, we need to find the support forces. It's good not to forget that. So we'll go ahead. We have AX and AY. I'll draw those in here. And we have B and the Y. And again, as has happened a lot, AX drops out, summation of forces in the X, that's the only one we have present, so it's equal to 0. Okay, we're going to reduce our distributed load into a single force. Okay, this is 8 kilonewton meters times 5 meters, that means it's 40 kilonewtons. It's going to be right in the middle here at 2.5. So for now, we're going to say this is 40 kilonewtons at a distance of 2.5 meters from A. So what I'm going to do here is take summation of moment about A. I'll come back to the range here in a second. Summation of moment about A equals 0 equals, okay, force at A drops out. We have a minus 40 kilonewtons times 2.5 meters. We have plus 20 kilonewton meters for the applied moment, and then we have plus By times our total distance here is 7. Okay, so we do the math here. We have 120 by 7. So we have By is going to be a not particularly round number, is 17.1 kilonewtons. So I'll write that in here. Then I can go ahead and do summation of forces in the Y equals 0. That means we have AY minus 40. The applied moment doesn't matter, we're adding forces, plus 17.1. This is going to give us a 22.9 for AY. All right, and just double checking. 22.9, that works. All right, so now I found my support forces. I can start talking about splitting this into sections and finding the internal forces. So again, we're going to look at 0 less than x, 0 is less than x less than 5, so the range between 0 and 5 meters. Okay, we are going to go back to our pure distributed load here. This is an important detail. When I cut this thing, as I cut this thing into 2 sections, okay, we're still going to have our forces applied here at 22.9, here at 17.1. We're going to have our applied moment of 20. Okay, the important thing is this cut here can happen anywhere between 0 and 5 meters. Okay, so that means no matter where we cut it, we're going to have, unless we cut it at one of the very extremes, we're going to have some of the distributed load on the left side and some of it on the right. Okay, this is an important detail, because if I had left this as a single force applied in the middle of our beam here, we would have, when we cut it, if we cut it at less than 2.5, the total distributed load would have been on the right hand side. If we cut it after 2.5, it would have been on the left. When in reality, if we cut it anywhere in between here, we're going to have some of the distributed load on either side. Okay, so when we start sectioning this, we need to go back to our original distributed load and then work from there. Just like we were doing when we were doing when we were doing internal forces at individual points. Now that we're doing shear moment diagrams, we still have to split this up, get this into two pieces. So we're going to have our shear and our moment, like that. Okay, looking at these two pieces, I think it makes sense to work with the left-hand side. Okay, this is an important detail here. This dimension is x, and this is 7 minus x. Okay, so this distance isn't going to be so bad. We need to replace this distributed load by an individual force. Okay, well, the individual force is equal to the area of that rectangle. Okay, the area of that rectangle is 8 kilonewtons per meter times x meters. So this force ends up equaling 8x kilonewtons. And it's acting at a distance at x over 2 from either side. Okay, the idea here is the amount of distributed load that's acting on this beam is dependent on the magnitude of the distributed load times whatever length is here. So it's going to be 8 times whatever length this is x. Okay, so at x equals 1, the force is going to be 8 kilonewtons, and so on up to x equals 5. We're going to have the entire 40 kilonewtons on there. Okay, so we can work with this to find our shear and moment. Okay, so we have 2 forces downward. We have 3 forces downward here. 3 forces acting vertically, so we'll go a summation of forces in the y equals 0. That equals 22.9 minus 8x minus v. That gives us that v equals 22.9 minus 8x. So I'll do that over here again. We're going to go 0 less than x less than 5. This is going to be v equals 22.9 minus 8x. Take moment. Okay, there's a number of different places I can take moment here. I don't want to bother with v times x. So what I'm going to do is I'm going to take the summation of moment about the cut. Let me rephrase what I just said there. Okay, if I had taken moment about A, I would have had the 22.9 dropping out, 8x times x over 2, and then v times x, which would have been this whole expression times x. If I take moment about this side, v drops out, and I have to deal with the 22.9, which is a lot easier than this expression. So I'm taking moment about the cut here. So about this point, okay, the 22 point, and this equals 0. So the 22.9 is causing rotation clockwise, so minus 22.9 times its moment arm is x. 8x is causing rotation counterclockwise, so that's plus 8x times its moment arm is x over 2. V drops out because we're taking moment about that end, and we just have plus m. So now m equals, this is going to become positive, so we're going to have 22.9 x minus 4x squared. Okay, so we get that up here. M equals 22.9x minus 4x squared. Okay. So that is our shear and moment here. Okay. So now we have to look at the next range. So taking this piece down. The next range, again, we've gone from here to here to here, nothing's changed. When we hit the end of the distributed load, okay, things change. The distributed load has gone away. And again, from 5 to 6, nothing changes, and then we hit this applied moment. Okay, so the next range is from 5 to 6. This segment look like this. Forces acting on this. We have our 22.9. Our entire distributed load acts on this half now. We have our 20 kilonewton meters here. And we have support force of 17.1 kilonewtons. All right. Well, we also have our internal forces, shear and moment, shear and moment. Okay, so now that the distributed load is entirely on one side, I can reduce this to just a single force, like we did way in the beginning when we were finding the support forces. So I'll draw this back in. And this is going to be 8 times 5 is 40 kilonewtons. At a distance of 2.5 meters from that edge. Okay, and again, this distance is x. All right, so now we have to do shear and moment. Okay, looking at either one of these, take a look at this. This is 7 minus x. Well, on either side, here we have two forces and the internal loading. Here we have a force and a moment and the internal loading. So it's going to be about the same in terms of that. I'm going to choose the left because I'd rather deal with a distance x than a distance 7 minus x. Again, it doesn't matter. You can choose either one. But I'm going to take a look at the left-hand side. So looking at the left-hand side here, I'm going to do summation of forces in the y equals 0 equals 22.9 minus 40 minus v. This gives me that v equals a negative 17.1 kilonewtons. So this is from 0, whoops, not from 0, but from 5 to 6. Take summation of moment. At this point, I might as well just take it about A equals 22.9 drops out. We have the 40 is causing clockwise, 0 goes, so minus 40 times 2.5. V is, it's causing clockwise, but we're going to end up with a negative there, so we're going to have negative 17.1 times x. Okay, we ended up with a double negative there. We found that the shear was, we drew the shear in the downward direction. We found a negative sign. That means it's actually in the upward direction. So it is causing clockwise moment. So we should end up with a net positive moment here. What I did is I said negative because the arrow is going clockwise, which should be negative. Plugged in the negative value, we end up with the same positive. Again, either way, it doesn't matter. Whether you keep the arrow in the sign or you flip the arrow and reverse the sign, you end up with the same result either way. So a moment here about A is going to equal, we need to add in moment there for the internal moment. M equals, I'm going to bring this over, 40 times 2.5 is 100 minus 17.1 x. Okay, so we have M minus 17.1x. Let me check some numbers here. It looks pretty good so far. Okay. Now then, this is that second piece. So now we know what's happening all the way up to length 6. We need to look at the third section. In the third section, we've included the entire distributed load on the left. We've gone and we've passed the applied moment, so the applied moment's now on the left, and we're just looking at this last section in here. So cutting it in this last section, we'll end up with a beam. This is between 6 and 7. End up with a beam that looks like this. 22.9. The distributed load has been reduced to a single force of 40 at a distance of 2.5 meters. We have an applied moment here of 20 kilonewton meters. And then over here, all we have is our 17.1 kilonewtons. We also have our internal forces, V, and internal moment, M, V, and M over here. Okay, distances, this is X. This is 7 minus X. Well, this time, with 3 forces on the left-hand side and only 1 on the right, I am going to go ahead and use the right-hand side. It's going to look a little easier. So I'm going to take the left side down. Just looking at this one piece here, summation of forces in the y equals 0 equals v plus 17.1. This gives us v equals negative 17.1 kilonewtons. This is from 6 to 7. We have v is negative 17.1 kilonewtons. Okay, not surprising that it hasn't changed between the 5 to 6 range and the 6 to 7 range, because we don't have any new forces in that section. We've applied a new moment, so our moment expression is going to change, but we haven't changed our forces at all, so our shear, our internal shear force is going to remain the same. Summation of moment. Okay, I'll take moment about the cut, that makes it easier, is equal to, well, we have 17.1 is going counterclockwise, so that's positive 17.1 times 7 minus x. Then we have our internal moment here is drawn in the clockwise direction, so we're going to go minus m. So we have m equals 17.1 times 7. And we're going to end up back at 120 minus 17.1 x. So we end up with m equals 120 minus 17.1 x. Okay, again, if you look at our moment expressions as we go through this section, we have 100 minus this, 120 minus this. Again, we've seen an increase in 20, which makes sense because we've just jumped up by an applied moment of 20 kilonewton meters. So at this point, all that's left is to draw the diagrams. So if I were to draw my shear diagram, and this goes 1, 2, 3, 4, 5, 6, 7, and this is in the x direction. Okay. And we start at 22.9, and we're going to end at negative 17. So I'm going to go 5, 10, 15, 20, negative 5, negative 10, negative 15, negative 20. Okay, you can set up whatever scale you like. All right, at 0, my shear, this is shear in kilonewtons. Okay, units on these are kilonewtons, these are kilonewton meters, kilonewtons, these are kilonewton meters, these are kilonewton meters. All right, so starting at 22.9 at 0, I'll do this in a different color. 22.9 will give me a value here. And then the shear is just going to decrease linearly by 8. So 22.9 minus 8 is going to be 14.9 at 1. Down 8 more, oops, is going to be 6.9. Okay, minus 22.9 minus 24 is negative 1.1. And at 4, negative 9.1. Should be able to do this math in my head, but I'm scared of making a mistake. 17.1, negative 17.1. So from 0 to 5, we have a nice linear decrease. Okay, at this point we're at negative 17.1, and it just stays there for the remainder. Okay, this makes sense. Our internal shear force is going to change gradually as this distributed load gets applied. Then it's not going to change until we get this last 17.1. And notice it starts at 22.9, it ends at 17.1, which will jump it back up to 0. Okay, so that's shear. Moment is going to be a little messier because we have some stuff that's not linear, in particular this first function here. Okay, again, I'm not too worried about exact plots here. I'm mostly concerned plugging in numbers and getting me a general curve. Okay, you will later on get into stuff where you have to find the minimum and maximum values, either in strength of materials or machine design if you go onto those courses. But for now, I just want to see what the basic curve looks like. So this is moment, and this is in kilonewton meters. Okay, when we apply, we have 0, so I end up with, this is going to end up being about 100. Here's the top here, so we're going to go. So this is 20, 40, 60, 80, and 100. Same thing downward. Okay, so plugging in values here. At 0, our moment is going to be 0. Easy enough. Again, a little bit of a sanity check. Your values should start at what they are at the end. We have no applied moment at this end, so there's no moment showing up at the left end in our diagram. Here we have an applied force of 22.9. It's a support force, but it's still a force applied to our beam, so that's 22.9. The other end, we have an applied force of 17.1. We end up at negative 17.1. That's fine. So here, we have no applied moment at either the left or right end, so in theory, we should end up at 0 again when we get back to to 7. So I'll make my tick marks here. And this is again x. All right, at 1, we have 22.9 minus 4 is 18.9. So that's right about here. At 2, we have 45.8 minus 16 is 29.8. At a value of 22.9, so at 3, we're at 32.7. Looks like we're leveling off here. At 4, we're at 27.6. Okay, so apparently I eyeballed my scale way wrong, but that's fine. And then at 5, we're at 14.5. Okay. At 5, we don't have anything, so we should get 14.5 again here. So 100 minus 17.1 times 5, okay, is exactly 14.5. That looks good. So at 6, is negative 2.6. And then at 6 here, we'll check this one. We should not get the same point. We should get a jump because we have an applied moment. Obviously it does jump by 20. But if you want to plug it in, it's 120 minus 17.1 times 6. And you end up with 17.4, which is obviously a nice jump of 20 here. And then at the end, 120 minus 17.1 times 7 does equal 0. Okay? So this thing, and it is important to show me shape, okay? This is parabolic. So from 0 to 5, we have a nice parabolic shape. 6 to 7, it's linear, and it jumps vertically by 20, and then linear back down. Okay. Worth noting here, we have this discontinuity at 20 where we have an applied moment. Okay, again, the scale got a little scrunched because I kind of I miscalculated the range on this, but it does show you the moment diagram here as we go from 20 up to the low 30s, back down to slight negative here just as we're getting to the edge of this, just before we get to this applied moment, but then the applied moment causes back positive. At the end, we end up back at 0. So again, it's a good idea at the end to kind of sanity check these things. Make sure you've got discontinuities at the applied loads. Make sure you're starting and ending at the values you should expect to. So that wraps up shear and moment diagram.